In the first part of this lecture, we talked about loading liquids in compression and tension, and I want to emphasize that when that happens, the force is acting normal to the area. So the force, I'll put an arrow here to highlight that, is perpendicular to the area upon which the force is being applied. And those little red arrows just indicate that the force is spread out over that area. In shear, that force is applied tangentially, so it's parallel to the area over which it's acting. And the only way you can apply a tangential force to a fluid is because of the property of viscosity. So in liquid, the intermolecular interactions cause the liquid to want to stick together a little bit. The molecules are not bonded as tightly as in a solid, obviously, so you can't think of them as springs like we did with the solid, but they do tend to stick together. Particularly water has big dipole moment, and it wants to be with other water. Water molecules want to stay together. With gases, the molecules are running into each other. They're hitting each other and they're transferring momentum, so they're interacting in that way. And it is these intermolecular interactions that allow the force that's being applied to one molecule or one layer of molecule, one area, to be transmitted to the next one and to be affect this in a tangential way. When we thought about a shear stress in a solid, I gave an example of how to imagine where the lines of stress, or how to think about where the lines of stress are of this cantilever beam. And if that beam were made up of planks and you applied a stress on the end, a force on the end, and that's put the beam in a shear stress, the lines of stress are going to be where the lower beam would try to slide out beyond the one above it, and so on. So that's how you can visualize where those lines of shear stress are. And the same thing is true in a fluid. This movie shows a flume, and dye is injected into the bottom of the flume. And the dye coats the bottom of the flume. It stays on the bottom of the flume because that layer of water is not moving. So when a fluid touches a solid, there's a coating that's put on the solid, and those molecules do not move at all. So this isn't heavy. It's not sitting on the bottom because it's heavy. It's sitting on the bottom because that layer of water isn't moving. That's called the no-slip boundary condition. So the very first coating is literally stuck to the solid. And then the one above it moves a little bit faster, and the one above that a little bit faster, etc., until you reach the free stream velocity. Understanding the relationship between the shear stress that's applied in a fluid and how the layers move, how the velocity changes and the different layers of fluid move, is explained very well in the video that I've linked here, and I recommend you watch it. And it's made by the Efficient Engineer. And the images I have inserted in these slides come from that video, and these in the next couple of slides. I'm just going to step through the basics of this. The upper left-hand panel shows the layers of fluid, and in this case it's like the flume that we just watched. The bottom of the image is where the fluid is contacting the solid. So that bottom layer isn't moving. Velocity is 0. And then as you move up the water column, each progressive layer is moving more rapidly. And the shear stresses between the layers are illustrated by these yellow layers, yellow arrows. The second panel actually draws a profile of the differences in velocity in those layers as you move up in the y direction. So this change in velocity is this delta u for a given
distance away from the wall is delta U over delta Y. And that slope, for a little change in velocity between the top and bottom of a layer and the thickness of that layer, is a lot closer to vertical when you're in the center of the stream, and it will be completely vertical if you're far enough away from the wall. All of the layers will be moving at the same velocity. And then closer to the wall, it becomes much more horizontal. So the little yellow layers illustrate the stress that is being experienced by each, the shear stress that's being experienced by each one of those layers. So the shear stress is much greater near the wall than it is in the center of the stream, where the layers are moving at a more similar velocity. For many fluids, not all, but for air and for water, for many common fluids, there is a linear relationship between the size of that shear stress and the rate of change of the velocity of the water. And that's Newton's law of viscosity, that you have a linear relationship that you can represent by some constant for the slope between the shear stress and the change in velocity. And this slope is called the dynamic viscosity and is represented by the Greek letter mu. Now, not all fluids are Newtonian, so blood is an example of a non-Newtonian fluid, and so is a solution of cornstarch, and I'll come back to those in a minute. This slide illustrates several important concepts and definitions, including the boundary layer, laminar and turbulent flows, Reynolds number, and vorticity. It shows fluid flowing toward and over a flat plate. Before that fluid reaches the plate, all of the lines of flow, these layers of flow, are parallel to each other. Once it hits the plate, then because of viscosity, the layers that are closest to the plate slow down. The one touching the plate doesn't move at all, has zero velocity, the no-slip condition. And then as you move away from the plate, the velocity keeps in each successive layer keeps increasing. This slide shows, the illustration shows blue squares. These are fluid particles, and it's really interesting to see what these fluid particles are doing. So the ones far away from the plate are unaffected. They retain their shape. But the ones that are close to the plate start to get deformed. It makes sense because the bottom layer is moving more slowly than the top. And so the top portion of this fluid particle, the angles change. So this is a shear stress and a shear strain. If you progress far enough along this plate, and that's in the x direction, those particles, those fluid particles, actually are rotating. And that rotation or spinning motion of a fluid particle, that's known as vorticity. Now you notice that there's a sort of an arbitrary definition. We call it the boundary layer, and it's defined as the distance away from the plate until the flow reaches some predefined percentage of that free stream flow, the flow either before it ever hit the plate or way out at an infinity, where the viscous forces aren't slowing it down. That distance, that boundary layer, is usually considered to be somewhere between 95 and 99% of that free stream flow. And it grows, so this is important. As you progress along the plate in the x direction, that boundary layer keeps growing. And you'll notice that there's sort of an abrupt transition. So the flow is initially laminar, but as it progresses, it becomes turbulent. And what that means is the fluid particle that was in this closest layer, not only is it rotating and spinning and has vorticity, but it starts mixing with the layer above it. And this mixing can result on it just taking off and ended up moving away from the plate. So that mixing is when that starts to happen, you no longer have these parallel layers of flow. That mixing is known as turbulent flow. So that's increasing as you move along the plate, the change from this laminar to turbulent flow. This boundary layer depends then on the distance you are along the plate, but it also depends on the viscosity of the fluid, and that's not surprising because that shear stress is basically the change in velocity with respect to the distance you are away from the plate is the definition, and the relationship with the stress that's applied is the definition of viscosity. So it's not surprising viscosity is playing a role in this, or involved in these equations. But it also depends on the density of the fluid and the velocity of the fluid. And these can be related in terms of what is known as a dimensionless constant, or dimensionless number, known as the Reynolds number. And that boundary layer then is approximately 5 times wherever you are along the plate, that distance x, divided by the square root of the Reynolds number. The Reynolds number is given by the density of the fluid multiplied by that free stream velocity multiplied by some characteristic length, so how far along you're looking at this along the x-axis, divided by the dynamic viscosity. Now I want to play a video for you.
In order to understand how viscous forces can influence the entire flow field, we shall look at what causes boundary layers, how they grow, how they respond to pressure gradients, and the difference in behavior of laminar and turbulent layers. Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer. The thickness of a boundary layer is sometimes defined as the distance delta from the surface to where the velocity u reaches some fixed percentage of the free stream value. For our purpose, we will use 95% of the free stream velocity to define the thickness of our boundary layer. The gradient of the velocity normal to the wall, delta u by delta y, times the viscosity mu is the wall skin friction or shear stress tau. The greater the velocity gradient normal to the wall, the greater the shear stress. Upstream, the velocity gradient is fairly large. Downstream, it is much less. This composite photograph compares the two velocity profiles. The smaller gradient downstream indicates the wall shear stress decreases along the plate. The growth of the boundary layer thickness along the plate can be explained by considering the time history of the vorticity within the boundary layer. States that the area integral of
There are a couple of more things I'm going to show you in that video, but first I want to discuss what you're going to see and why you're going to see this. So we're going to look at the boundary layer again, but not on a flat plate, not over a flat plate, but over a curvilinear surface. And the important point is that when you have a curvilinear surface, like this bomb-shaped surface, there's going to be both a pressure force exerted on that, as well as these tangential shear forces that we've been discussing. And the relative importance of these forces depends very much on the shape and where you're looking at the shape. So for example, over on the left-hand side, I've shown an illustration of just a flat plate where the broad side of it is facing into the fluid. So there's a large pressure generated, a large compressive force generated on the upstream side of that plate, and very little compressive force on the downstream side. And there's almost no friction force. There's almost no tangential forces placed on this plate. They're there, but they're very small relative to these normal forces. If you turn the plate on its edge so that the thin side is facing the flow, then there's a lot of this friction or tangential shear stress induced in the layers of fluid as it flows over it, but almost no pressure force, right? Because the profile facing into the flow is so small. So if you look at and this comes from that second video on drag that is on Canvas. These are just screenshots from that video. But if you think of this bomb shape and the pressure force is normal, right? So it's pointing directly down onto the surface, and the friction force is tangential, as illustrated. That can be divided into components. They can be divided into components. And I've done that with the little red arrows for the pressure. The component, the horizontal component, the part that is running parallel to the flow, that is pushing against the bomb moving forward, right? That is opposing the flow. So that is slowing the bomb down, that component of the pressure. However, when the pressure as the fluid particle is moving around the surface down in that middle image, the pressure is pointing straight down at this point, just straight down onto the surface. And so there is no horizontal component. So the pressure force doesn't contribute anything at that point to opposing the flow. And when the fluid particles move even farther behind on that tail, now there's a component of the pressure force. It's in the horizontal direction, but it's pointing the opposite way. So it's actually helping the bomb to move forward. It's actually contributing to forward flow of that bomb. So whether the pressure force is opposing, not making any difference, or actually facilitating this relative movement depends very much on the shape of it and on the orientation of those forces. The sum of the normal forces and the tangential forces are equal the net inertial forces. So if the normal force gets bigger and the tangential force gets smaller, then most of the total inertial forces are due to that normal force. And this is known as Newton's equation of motion of a fluid. So the normal forces plus the tangential forces equal the total net inertial forces acting on that fluid that determines its behavior. So in this video, you're going to see what happens to the boundary layer because of the change of these, the direction of the normal forces, the pressure force. The key things that I'm going to show you in this movie are what happens to the boundary layer when it encounters a curvilinear surface that causes the fluid to converge. That's illustrated in this left-hand corner. You'll see the flow going through this narrowing of the tube, and you want to look on the bottom part of this to see what happens to that boundary layer. So spoiler alert, what happens when it moves into the smaller portion of that tube, the fluid starts flowing faster and the boundary layer gets thinner. So there's more shear stress in the wall. There's a higher shear stress, and most of the vorticity is therefore located very close to the wall. This is called a favorable pressure gradient. In contrast, when the fluid is diverging, that creates what's called an unfavorable pressure gradient, and the boundary layer actually pulls away from the wall and separates, and you get reversed flow, and the point of separation is called the separation point. And then you'll see some turbulent flow, and the key thing about the turbulent flow is that it retards that point of separation. It helps to keep the boundary layer attached to the wall. So those are the key points to take away from this movie. Curvilinear surfaces are going to create these pressure gradients. You're not just dealing with these horizontal shear stresses, you're dealing with pressure gradients also, and those pressure gradients can be favorable in terms of keeping the boundary layer attached to the wall and in terms of creating a thin boundary layer, or they can be unfavorable in terms of the boundary layer detaching from the wall and separating.
We have seen the behavior of two-dimensional boundary layers on a flat plate in a uniform velocity field. So far, the pressure gradients in the flow direction have been negligibly small. However, in most flow situations, there are regions of decreasing pressure and regions of increasing pressure in the flow direction. We will examine these two flow situations separately. First, the case of a decreasing pressure or favorable pressure gradient in the flow direction. We will use this 2-to-1 flow contraction and watch the boundary layer along the flat side. The upstream boundary layer is growing slowly as it enters the contraction. After the contraction, the boundary layer is thinner. Note that the distance from the wall to the streamline downstream is about half what it is upstream, because the two-dimensional flow contracts 2-to-1. In the contraction, the effect of the pressure gradient in the boundary layer is to enhance the already high shear stress or vorticity concentration very near the wall. It is as though a new boundary layer were being generated within the old. The combined profile at the exit is relatively thinner because there has been little time for growth of the new boundary layer by viscous diffusion. Using vorticity arguments, we can see that the vorticity added to the boundary layer by the contraction has had little time to diffuse. So downstream, a larger percentage of the total vorticity is nearer the wall. This results in a relatively thinner boundary layer and higher wall shear stress. On the other hand, in a divergent channel, the boundary layer becomes thicker, with a corresponding decrease in wall shear stress. In this case, we have an unfavorable pressure gradient. The increasing pressure associated with a decreasing mainstream velocity decreases the velocity in the boundary layer, so velocity gradients and shear stress are less, and the boundary layer is thicker. At a larger angle, the decrease in velocity is so great that somewhere along the wall, the velocity gradient normal to it becomes zero, accompanied by a local reversal of flow immediately downstream of the point. The fluid, which was in the upstream boundary layer, is no longer in contact with the wall and is separated from it by a region of reversed or recirculating flow. The boundary layer is said to have separated. Point on the wall where the fluid in the upstream boundary layer meets the fluid from the region of flow reversal is called the separation point. The wall shear stress is zero there. Here, the point of separation of the laminar boundary layer is near the first wire. The boundary layers we have seen so far have all been laminar. However, in most practical high Reynolds number situations, the boundary layers are not laminar. Rather, they are turbulent. Flow along a cylinder filmed with a high-speed camera can show the stages in the transition of the boundary layer from a laminar one to a turbulent one. A slight adverse pressure gradient causes transition to occur within the field of view. The steps in the transition are very complicated and interdependent. Of nearly two-dimensional waves, the Thomaine-Schlichting waves, followed by the appearance and growth of three-dimensional disturbances associated with streamwise vorticity. Then turbulent spots can be seen. And finally, fully turbulent flow appears. Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way. This boundary layer around a channel bend is made turbulent by placing an obstruction in the layer upstream. The obstruction stimulates the naturally occurring processes and hastens the onset of transition. The flow here is all downstream. Removing the trip rod results in separation and backflow. Bubbles accumulate at the separation point. In this diffuser, which was used before, we have made the bottom boundary layer turbulent by inserting a trip rod upstream. The turbulent boundary layer is able to withstand the adverse pressure gradient in the diffuser, while the laminar layer along the top wall is separated, allowing reverse flow. These timelines show that in the turbulent boundary layer, there is no separation. The overall flow is downstream. To see why a turbulent boundary layer can withstand a larger unfavorable pressure gradient without separating, we shall again examine the flow along a flat plate. The boundary layer on the bottom side is laminar and two-dimensional. On the top side, the boundary layer has been tripped by a wire placed well upstream. Unsteady motions in the turbulent boundary layer are three-dimensional. Some of the motions are perpendicular to the plane of view. These timelines correspond closely to the instantaneous velocity profiles for the two types of boundary layers. Superimposing a number of displacement lines enables us to obtain a mean velocity profile for the turbulent layer and the laminar layer, and at the same time gives an experimental notion as to where the fluctuations occur and how large they are in the plane of mean motion. In this photograph, we can compare mean laminar and turbulent profiles. Here is the laminar one, the turbulent one. And here they are superimposed. The velocity gradient normal to the plate is larger for the turbulent layer, and it therefore has a larger wall shear stress or drag. The circulation is the same for both layers. Both boundary layers therefore contain the same amount of vorticity per unit length of the plate. However, the distribution of vorticity in the two layers is very different.
Let's apply some of what we've learned to flow around a cylinder. So you're looking at a cylinder end on in this illustration. And what is shown, there are three streamlines. The middle one comes to a stop right in the upstream portion of the cylinder. And the point at which it comes to a stop is known as the stagnation point. So the velocity is 0 at that point. And then the stream subdivides. Some of it goes to around the top, some of it's going around the bottom. And this shows two streamlines. They have the arrows moving around the bottom of the cylinder. The third line, which doesn't have an arrow, is the boundary layer. That's the edge of the boundary layer. Okay, so that's somewhat arbitrary. That's set at maybe 99% of the free stream velocity. So that's the point in the fluid where the velocity has returned to almost the free stream velocity. Now, as we just mentioned, as you've seen, the normal forces exerted on the cylinder from the flow from the fluid particles in the flow are maximal in the front of the cylinder at this stagnation point. And then they're minimal at the top and the bottom. And in contrast, the tangential forces, these viscous shear forces, are minimal at the front, but they're increasing on the top and the bottom. And this illustration shows that. It shows how the shear stresses are changing around the shape of that cylinder. Because of the shear stresses, we have this vorticity that is set up in the fluid particles. So the bottom part of the particle is not moving, or the part that's closest to this cylinder is not moving as rapidly as the part that's farther out towards the free stream. And so you get this rotation and this deformation, this vorticity. And at some point, because of the curvature of this cylinder, in part, there's a place where the flow detaches, that boundary layer detaches, and you get a reversal in flow. You get what is sometimes also called the backflow. And then in this area where the flow has detached, right, you've got all this turbulence and all of these eddies. And those eddies and that backflow are taking energy away from the system. And this is I think a really lovely and poetic way to put it. It says, the big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So the energy is basically taken away from the momentum of the flow. Either the cylinder could be moving or the flow can be going over the cylinder. It's relative, right? And it's being dissipated in these eddies, which eventually become heat. Now, the point at which the detachment occurs, if it occurs at all, depends very much on the Reynolds number. So if you have a very, very big sphere, the characteristic length, or cylinder, is the diameter. The Reynolds number will be big. Or if this system is working in a very slow flow regime, then the Reynolds number will be very small. If the viscosity is high, the Reynolds number will be small. So these, the length, the characteristic length, the velocity, the density, and the viscosity, that combination determines this Reynolds number. And the Reynolds number then determines whether you have this separation of a boundary layer. At low Reynolds numbers, something less than 10, there is no separation. And because of that, there's a lot of recovery of that normal force. So the pressure that you're pushing on the front of the cylinder in the upstream side is recovered by the pressure pushing on the cylinder on the downstream side. And almost all of the drag in this low Reynolds number regime, almost all of the resistance to flow comes from this tangential stress, this viscous, that results from the viscosity of the fluid. At slightly higher Reynolds numbers, you get a little bit of detachment. You start to get a vortex that is attached to the solid. It just sits there. If the flow is coming from the left, they're going to spin in the opposite direction. So the top vortex is spinning clockwise and the bottom one counterclockwise. And at a little higher Reynolds numbers, these start to detach. And when they do that, that's known as the von Karman vortex trail, or von Karman street, after the scientist who first identified that this would happen and study it. And that at even higher Reynolds numbers, turbulence sets in. You get a turbulent boundary layer. Now look at the difference between the thickness of that boundary layer when the vortices are being shed, and you've got the von Karman vortex street, versus once the boundary layer becomes turbulent. Now the wake is much smaller, and the system is actually losing less energy to those vortices. So I'm going to play a simulation and let you see how this develops as Reynolds number increases. This next slide I'm going to show you is one of these von Karman vortex trails, but it's in clouds. It's actually been formed from the tip of a volcano that's sticking up into the cloud layer. So this is a photograph from NASA, and this is an island in the southern Indian Ocean, down in the Antarctic. And you can see at the beginning of this von Karman vortex trail the tip of a volcano with snow on it sticking up into the clouds, and then that the shedding of those vortices. Now it's important to realize that they're spinning in the opposite direction, and fish have figured this out, and they use these von Karman vortex trails. Like a rock sticking up in a stream will create these the same effect, and they use these to save energy. And I'd like to play a photo, or play a movie of some fish that are in a lab in Florida, and they found one of these trails, and they're hanging out in it, and this is saving them energy. So as these eddies, if you think about the eddies, if you look back over on the illustration where the Reynolds number is changing, and you think about this third one down, the eddies on the right side of that fish's body are moving in a clockwise direction, or those fish, and that is propelling the fish forward, and the ones on the left side are counterclockwise, and that's again propelling the fish forward. So that they can hang out in that middle line in between these two shed eddies and save energy. So what is even more remarkable is that dead fish can do the same thing. Here's a dead fish swimming. So simply by the virtue of its location, the flexibility of its body, and its streamlined form, it's literally swimming upstream, even though it's dead. It's amazing. I would like to turn our attention to some mechanisms and adaptations that we see in lots of animals that are both either using air or water for locomotion that help to keep this boundary layer attached, to prevent this boundary separation, and thereby reduce drag. And these animals are all high and medium Reynolds numbers animals, right? So they're working in a medium to high Reynolds number. And the adaptations or mechanisms I'd like to look at start with the shape of the animal, a fusiform shape, sort of that bomb shape that we saw in the movies, or where one side is maybe flattened. So in water, they're considered hydrofoils, in air, they're considered airfoils. But the key part of this shape is really what's going on in the back part of it, sort of the design of the derriere. And then I want to look at a roughened surface, a tripping. Basically, we saw this in the movie when the boundary layer is tripped and turbulence is induced. It helps to keep the boundary layer attached. We'll look at some vortex generators leading at slots and slats, and some amazing examples of where the boundary layer is being sucked onto the body. So let's start with this fusiform shape. A long tapered tail allows the fluid to gradually decelerate in the rear, so that there's little to no boundary separation that's occurring. And there's a wedge-like closure of fluid behind the object with very little energy lost then in the wake. Instead, that energy reemerges as a forward-directed pressure from the rear. And that nearly cancels out the normal force at the front, that dynamic pressure at the front that was opposing flow. So almost all of that momentum is recovered if you have the right shape. And this slide is illustrating more or less the same things we looked at with the cylinder, where you have the stagnation point, a development of the boundary layer, which thickens, a transition to turbulent flow, a thickening of the boundary layer, but it stays attached. It stays attached better than it would if the curvature were greater. And then a very small wake. This makes a tremendous difference. This makes a tremendous difference. So this is from the movies, one of the movies I asked you to watch. This is the very last one at about 5 minutes into the movie. And the scientist does an experiment where he puts this airfoil into a flow and measures the drag, measures the resistance to flow, and then puts a wire. And these are drawn to scale of this dimension. These are drawn to scale, and finds that little teeny wire has equal drag to that much bigger cross-section. So at high Reynolds numbers, these streamlined objects have almost no pressure drag. They recover almost all of that pressure momentum, and they are basically Newton's equation of motion is made up almost entirely of the inertial forces that are equal to this skin drag. The fact that this fusiform shape is so effective at eliminating or almost eliminating that pressure drag explains its convergent evolution. This is one of the most striking examples of convergent evolution that I know. So we see this, of course, in many fish. Any fish working at a high Reynolds number that's swimming fast has a fusiform shape. If they're not at a high Reynolds number, maybe they've evolved for something else. They're not swimming fast, right? But all of the animals that are swimming fast have this fusiform shape. And then we see it convergently evolve or re-evolve in the descendants of the fish that went onto land and then went back to the water. So this happened in reptiles a number of times. You've got plesiosaurs and ichthyosaurs that have re-evolved this fusiform body shape. This has happened in marine mammals, such as this porpoises and dolphins and whales. This has happened in other marine reptiles that have returned to an aquatic lifestyle, like this marine turtle, and it's happened in birds. So as illustrated by the penguin, but it's also present in flying birds, right? This same principle, it doesn't matter whether it's water or air. All that matters is the Reynolds number. If the Reynolds number is high, then there will be very, very strong selection for this fusiform shape. And what that does is to reduce the pressure drag, so that the only real drag these animals are worried about or have to overcome then is the skin drag, that tangential surface drag.
This slide shows three mechanisms that generate lift. So if the airfoil or hydrofoil is asymmetrical, so that it's flat on the bottom, then fluid flows more rapidly over the top, and that reduces the pressure on the top of the foil by the Bernoulli effect, and that generates lift. Lift can also be generated just by the angle. So if the foil is tilted up relative to the wind, as you've seen, as is displayed here, that angle alpha is called the angle of attack. Well, there's going to be more of a normal force, a greater normal force on the bottom of that cord pushing it up than there will be on the top. And so that's another mechanism by which lift is generated. And then this figure 2.1 shows a symmetrical foil, and that's at an angle of attack, and that's causing more rapid flow over the top, just that angle of attack, but it's also causing the redirecting the flow. So some of it is pointing down. It's pushing the air. It's literally pushing some of that air down, and that means that the foil is being pushed up when that happens. And because the flow is moving at different speeds on the top and the bottom, that also induces a vortex. When the fluid particles come back together, they're twisted now, and so you get a trailing edge vortex.
So this is a fighter jet, and it is the pressure above the wing is reduced enough that the air is condensing. So the water vapor in the air is actually condensing, which shows you pretty beautifully the distribution of how the pressure is decreased over the wing. This slide illustrates the shed vortex, that trailing edge vortex, and the movement of the air down as the plane or the solid moves up. So then this is called, pushing that air down is called downwash. And it's equivalent, the downwash is equivalent to the mass of the plane being pushed up. The shape of the foil matters quite a lot as to whether or not the object is going to stall with the given angle of attack. So something that has a very thin foil, such as this fighter jet, has to move really fast in order to generate enough lift. So it would tend to stall much more readily than the highly cambered wing of this stall airplane. So it could fly a lot slower and not have that reversal in the pressure gradient and stall. This movie shows a plane that's increasing its angle of attack until it stalls. You're going to be able to see what's happening to the backflow on the wing because there's strings attached to the wing that will illustrate the direction of the flow. Notice the backflow starts at the trailing edge, and it also starts close to the fuselage.
So one way to prevent that boundary layer separation and that reverse flow or that unfavorable pressure gradient is to, as we've already seen, to generate turbulence. And one way that was shown in the movie was a tripwire that generated turbulence. So if you disturb that laminar flow, it will it can generate these small vortices, and that turbulence in the boundary layer then helps to keep the boundary layer attached. And that's what you're seeing here. These are actually called vortex generators. You're seeing them on the edge of this airplane wing. You've probably, if you've flown, when you look out the airplane window, you've seen these on the wings, almost certainly. And so basically it's preventing or reducing the point of detachment of the boundary layer. A few years ago, a friend of mine, a man named Frank Fish, who happens also to study fish, was in a curio shop, and he looked at a carving of a whale, a humpback whale, and he noticed these tubercles on the leading edge of the whale's flippers. And he thought, that can't be right. That's not very streamlined. That the artist screwed up. So then he went and looked at pictures of humpback whales, and sure enough, there are all these ridges on the front of their flippers. And he wanted to figure out what they did. So he undertook a series of studies that show that these are vortex generators. And they help to keep the boundary layer attached to this whale's flippers. Now these whales need this in part because of their feeding habit. So they tend to swim in very tight circles and blow bubble nets that trap and confuse their prey. So they need to be able to swim at a very high angle of attack in these tight circles. And because of that, they need these extra devices on their, they've evolved this extra mechanism to keep the boundary layer attached so that they can have these steep angle of attacks and not stall, basically. So he showed this by collecting a number of flippers from whales that had been killed in accidents and things. He didn't kill any animals, of course. And making models. So he physically put these flippers into flumes and studied their fluid flow. And he teamed up with a mechanical engineer who's shown here. And they made a series of models to show that indeed these the shape of this flipper was creating these vortices that facilitated boundary layer attachment, right? So they prevented that adverse pressure gradient from forming and kept that boundary layer attached to the flipper. They've actually started a company, and they're making these sort of leading edge tubercle shapes in, well, here you've got a surfboard. This is flippers. They're putting them on the rudders of boats, on race cars, on the blades of helicopters. This is a fan that it reduces the drag on fans and creates significant energy savings. And Frank actually won a prize, an international prize for this work that he's done. It was inspired really by him just thinking the artist had made a mistake in their sculpture. But these tubercles, they increase stable lift. So the foil is less likely to stall, and they keep the drag low at these high angles of attack, or high pitch angles. And they increase the performance, the generation of lift and the performance at low speeds. Basically, that's their sort of why they've been so successful. But they're not only found on these humpback whales. You see them elsewhere now that he's looking in the head of a hammerhead shark, on the dorsal fin of marine mammals, and even this, the vibrissae, or the whiskers of marine mammals. And these are sensory organs, right? So the way that they shed vortexes is very important, and if that can be controlled, then their whiskers are going to work better. I think those are really cool examples of how these basic physical principles of fluid-solid interactions give rise to fusiform body shape and vortex generators in the biological world. The surface roughness also has been undergone selection for facilitating the attachment of the boundary layer in some animals. And before I talk about an animal, I just want to show you a movie of a golf ball. I know this was discussed in that first video, the first NSF fluid dynamics video on drag, but I think this next movie is fun.
You are flying next to a golf ball, sailing through the sky. It's long been known that pocking a golf ball with small dimples lessens the effect of air drag as it travels. But precisely how this happens has never been quantitatively understood. Now, researchers from Arizona State University and the University of Maryland have visualized the airflow with a supercomputer. Moving into about 45 degrees from the leading surface of the ball, we can see a number of trains of vortices have developed. These lines of whirlpools follow the scallops of the dimples in the direction of the airstream. Closing in now on the air's behavior around just a pair of dimples, we see the airflow evolve from front to back. Watch now within a single dimple as the air detaches and shears away, varying with the stream's direction. we see that the cumulative effect of the vortices pulls air down onto the ball, delaying energy-wasting separation. Golf balls with dimples turn out to be almost twice as slippery as those without. But how many dimples should there be? How deep? What shape? Since there are no rules regulating these factors, sporting goods companies are free to tee up new patterns. But detailed numerical visual analysis, like we see here, will no doubt play a big part in golf ball design from now on. For LiveScience.com, I'm Dave Brody.
The scales of shark serve as, much like the dimples and ridges of a golf ball, to generate vorticity and keep the boundary layer attached. So in the bottom left-hand corner, you're seeing a scanning electron micrograph of these scales from a short fin mako shark. And there have been a lot of studies done now showing that they reduce this negative pressure gradient. And some of them, there's a sort of a passive mechanism as the shark swims faster and pressure is reduced over their hydrofoil, right? This reduced pressure actually sort of pulls the scales out into the water column a little more. So there's sort of a passive mechanism, which they almost like flaps on an airplane raising, but they raise out into the water column a little bit more, and they produce, the faster they swim, the farther out they, and I don't know if all sharks do this, but I do know it's been found on some. So they stick out, and then they create these little small vortices. You can see that in a little small vortex right behind the scale. And that serves, again, to push that boundary layer down onto the surface. And then figure 8 is showing that not only is there a vortex formed behind the scale, sort of on the trailing edge, but because of the ridges, because of this, the 3 ridges, there are vortices formed down in those valleys as well. So there's several different mechanisms by which these scales are facilitating adherence of the boundary layer. These scales and studies of these scales are inspiring new designs in vortex generators to be used on human-made crafts. So it's a really cool example of how we have a lot to learn from Mother Nature. Finally, I'd like to turn your attention to some leading edge slots and slats and suction, and how this helps keep the boundary layer attached. And I'm going to first show you another clip from one of these fluid dynamic films, and then I'll show you examples both on man-made devices and in nature.
As the boundary layer develops around any body of appreciable curvature, the point of separation rapidly moves forward from the zone of maximum pressure rise at the rear to the zone where deceleration first occurs. As a matter of fact, no change in boundary alignment is really necessary, just so long as there is a shear zone of low velocity and an adverse pressure gradient, such as prevails beneath the front of this undulous surge, moving slowly against the flow. Separation leads to 3 important occurrences. First, it changes the anticipated flow pattern. For instance, this channel expansion obviously does not cause the flow itself to expand as rapidly as desired. Secondly, it produces boundary drag, thereby expending energy through the generation of eddies, which rapidly transform to turbulence. Finally, it can lead to oscillation of the flow, with a corresponding pressure fluctuation, boundary vibration, noise generation, and perhaps even structural damage. Though separation is very essential in the operation of parachutes and baffles, it should in general be avoided by the control of the boundary layer or the pressure gradient, or of both together. If the boundary moves with the flow, for example, the retardation by shear is offset, and separation obviously is prevented. Much the same elimination of separation is realized if, as is now beginning to occur, fluid is discharged tangentially into the boundary layer region through boundary slots. Even better results will next be seen to obtain as the boundary layer fluid is sucked into the slots as rapidly as it is retarded. A change in the pressure field as a whole.
As that video showed, if fluid is pushed tangentially into the boundary layer, it reduces negative pressure gradients and reduces detachment. It impairs detachment. And one way to do that is seen here. This is called a leading edge slat and slot. So the slat is, this is running the chord length of the wing. So the chord is the distance from where the wing attaches to the body fuselage and out to the tip. That's called the chord. So this slat would run the entire length of the wing, and it's wider at the mouth than it is at the back, so it's wider where the slot is labeled, and that acts as a funnel. So air enters that, and then it starts to narrow, and that speeds up the flow, and then that is directed down onto the boundary layer. And these allow planes to fly more slowly without stalling. So for a given angle of attack, it reduces the airspeed that they have to be at before a stall sets in. This is a biological example of a leading edge slot and slat. So this is the elula on a bird wing. And you can see without the presence of that slat that there's unfavorable pressure gradients and reversal of flow. But when the elula is present, then you've got this much better adherence of the boundary layer. A very interesting example of potential suction of part of the boundary layer into a slot, and then injection of momentum into the boundary layer is found in this fish. This is the castor oil fish, and they are a sit and wait predator. They're very rapid sprinters. And the integument is quite unusual. This is an illustration of their rather unusual integument. They have two different types of scales, the ctenoid scale and a cycloid scale. The ctenoid scales are sticking up and are almost certainly acting as vortex generators, much as the ridges on the shark scales are acting as vortex generators. In addition, these scales have this subdermal skeleton on them, and they form a network of chambers under the skin. And there are pores associated with these chambers. And it's thought as the fish is swimming side to side, right, it's bending one side of the body and then the other. It's compressing, it's loading and compression, this integument at the same time that it's moving forward and then in tension. And it's thought to be pumping water into and out of these chambers. And so on one side, when it's expanding, it's thought that fluid is pulled in, and that's going to be fluid from the boundary layer, right? So that's going to act, as we saw in the movie, when you suck the boundary layer in, it's going to help to keep the rest of it attached. And then when the flow is ejected, it's going to impart momentum to the boundary layer. So both of these devices, the sharp ctenoid scales that stick out, and then this very odd subdermal network of caverns, is probably an adaptation to keep the boundary layer attached. Those are a few adaptations to keeping boundary layers attached for animals that are working at high Reynolds numbers.
I have a few more things I would like to share with you, but again, the movies I think that are embedded in this PowerPoint are not running quite right, so I'm going to stop here and follow up with a third lecture.